You got to know your. I've already used it out in the past, so I know what I like. Just type on what's wrong with it. I think you're just dying.
You can't go wrong with a comb over.
So I think you're just weird. You don't like, oh, you don't like long hair. I thought you said you don't like dry hair. You get, no. There you go.
Can I even?
Okay, page 20 in your packet. Okay, go ahead and copy down these notes. A lot of this will feel intuitive because we've kind of been doing sign lines with velocity, particle motion. So a lot of this will connect in very similar ways. Okay, so what does a derivative represents? Derivative is the slope of a tangent line to a curve. When a function is increasing, that means I have a positive slope, then what's common about the derivatives is that my f prime is going to be greater than 0. So f prime greater than 0 indicates positive slope, but f prime is less than 0, that indicates a negative slope. So likewise, when f prime is greater than 0, my function is increasing. When f prime is less than 0, my function is decreasing. If f prime is equal to 0, that means my function is a constant. It's either going to be experiencing potentially a relative max, a relative min, or it's just where a horizontal tangent is. So maybe a graph where the slope is flattening out for a moment and then rising, or peak or valley. Those are all slope zeros. Okay. Slope zero doesn't guarantee a peak or valley, but it is many times a candidate for max and mins. So if we want to find increase, decrease, and relative max and relative mins, we're going to start, this is what we call the first derivative test. Basically, we're just creating a f prime sign line, and then we're going to populate the sign line, and we're going to get an idea as to how the shape of the graph is formed, where the graph is rising, when the graph is falling, where the graph is going to be experiencing potential slope zeros and potential max and mins, peaks and valleys, relative max and relative mins. So we always are going to start off by setting f prime, finding f prime first, and then setting f prime equal to 0. Remember that we have to consider both the numerator and the denominator set equal to 0 separately, because we know that if a denominator of a derivative is equal to 0, that could be a location where a slope is undefined. And slope is undefined could be a sharp turn, and a sharp turn could end up being a relative minimum or relative maximum for our graph. Okay. Next step, we're going to put all these critical points onto f prime sign line, just like how we were doing with velocity sign line with particle motion. And we're going to plug values into f prime to determine to populate the sign line. So we're going to pick values in each subinterval to plug into f prime, and then we're going to be able to indicate whether each region is a positive slope or a negative slope. And whenever there is a change from a positive slope to a negative slope, we can confirm that there's a relative max at that point. Whenever the slope changes from a negative to a positive, we can confirm that there is a relative minimum at that point. Okay, so let's do example 1, and we're going to try to gather the movement of the graph without looking at the graph itself, just relying on f prime and the f prime sign line. Okay, so number 1, determine the interval in which our function is increasing and decreasing. Locate the relative extrema. So extrema is just the plural for extremum. So just relative max and relative min. That's what extrema could represent. So anytime we're talking about increase, decrease, let's also find relative max, relative min. So we're going to go ahead and find f prime first. Everything that we need is going to be from f prime. So we can just do power rule for each of these terms. 1/3 x cubed becomes what? 5/2 x squared becomes and then minus 6x becomes 6. Okay, we're going to set f prime equal to 0 to find our critical points. Normally, we'll set the numerator and the denominator equal to 0, but there's no denominator, so just the numerator. So multiplies to be -6, adds up to be 5. So 6 and -1, so x plus 6. Solve for x, we get 1 and -6. So now that we have our slope zeros, we're going to place them onto our f prime sign line. So we know that these are places on the graph where the graph is experiencing slope 0, but we don't know whether it's a slope 0 with that's a relative max, a slope 0 that's neither, or slope 0 that's a relative min. And also, we don't know the exact behavior in each of these subintervals, so we're going to test each subinterval. Okay? The way we're going to test is we're going to choose values in each subinterval to plug into f prime. So let me test -7. I'll test 0 here, and I'll test 2 here. So I'm just you can pick any number you want in each subinterval. I'm just going to try to pick the smallest number that I can find, or the number closest to 0 that I can find, because those are, the smaller the number, the easier it is to usually plug in. I'm going to plug into f prime. Either f prime is fine technically, but I like to put it into the factored form because it's easier for me to gather the signs without having to do a bunch of calculations. So -7 for x. I get negative times a negative. 2 negatives makes positive. So I know that my graph is going to be experiencing a positive slope here. And I like to give myself a bit more visual with my behavior. So I'm going to use an arrow that is showing me positive slope. Okay, plug 0 into my f prime. 0 plus 6 is positive. 0 minus 1 is negative. Positive times negative is negative. So I know that this entire region here, my graph is going to be experiencing a negative slope. I'm going to show a line that is demonstrating a negative slope. Just kind of helps me visualize how my graph is flowing and in terms of how the graph is looking. Okay, plug 2 in. 2 plus 6 is positive. 2 minus 1 is positive. 2 positives makes positive. So these arrows I think are helpful because it kind of helps me see, oh, this is a graph that is rising. What's going to happen at -6? If it rises, follows by falling. There must be a what here. Okay. Relative maximum. And then it's going to fall and it's going to rise after that. So that means at 1, we should be expecting a what? A relative minimum. Yeah. Right. So on the AP exam, if they ask you to identify increase, decrease interval, relative max, relative min, they may also ask you for because statements or to justify your statements. So here's how we can justify our statements. Let's do our relative max, or sorry, our increasing first. So which interval is our graph increasing? To -6, and then from 1 to infinity. Now, once you identify your test points, you're not going to use them in your interval statements. So make sure that those are not used. You're only using the infinities, the -6, and the 1. Okay, so we can say our function is increasing. From -infinity to -6, union, or you can do comma, 1 to infinity. And then here's our because statement, is because f prime is greater than 0. So we want to make sure that we can write out those justifications. If I ask you for justification on the quiz, I'm looking for this because statement, because f prime is greater than 0. And where would you say the graph is decreasing? -61. And the reasoning is because f prime is less than 0. Okay, there's a relative max where at x equals -6. What if I ask you for the full order pair? Where would you find the relative max location? Plug it to the original. Yeah, so original will give me location. So this case, but for now, let's just identify the x value. And our reasoning would be there's a relative max because f prime changes from a positive to a negative. So this is our line of reasoning, our because statements for relative max and relative min. We have to indicate the order of sign change. Likewise, there's a relative minimum at x equals 1 because f prime changes from a negative to a positive. So this is how I went ahead and I found the y values, but the y values are coming from the original function. So you can copy that down, but you can use your calculator on the quiz. So if I ask you to find that y value, you should be able to plug it back into the original function. Okay, next page.
With the relative max of the statements, can I read like this? I mean, I started because I was running out of room, but if I write it like that, would that be?
F
prime.
Yeah, I'll prefer that you write it in more this way.
Yeah, I was just running out of room. If I write it like that, you say if we'd be fine.
If you run out of room, then just use a separate sheet. Then
Okay.
yeah. But okay, example 2. Everybody good with page 1? All right, number 2. Determine the interval in which our function is increasing and decreasing. Locate relative extrema. So we're going to go through the same process. We're going to find f prime. From f prime, we're going to find our critical points. From our critical points, we're going to populate our slope sine line and then indicate. But to get to f prime, we have to go through what? Quotient rule, okay? And then after we find our derivative, we should get a numerator and denominator, right? So you're going to set both the numerator and the denominator equal to 0 separately. Now, just before you go through this process, do you see any discontinuities with this graph? Okay, what's happening at 3?
Over 0.
There's a vertical asymptote. Now, this vertical asymptote will show up in your derivative, even though that vertical asymptote has no chance of being a relative max, relative min. We still want to populate it onto our slope sine line because it can still help separate our intervals of increase and decrease. So even though a critical point has no chance of being a relative max, relative min, make sure you still include them on your slope sine line. Okay, try that. So find f prime, go through quotient rule, find all your critical points from both the numerator and denominator, and then start populating your f prime sine line.
So are critical points the same as roots?
Same as when I think of roots, I think of x-intercepts, and those come from the original function. So the critical points that we're concerned with is going to come from f prime or f double prime.
But we're basically getting the roots of,
Yeah, we're getting the roots of f prime, right?
but they're not roots of it.
But it's not roots of f of x. The roots of f prime is going to be where the slope is either 0 or undefined. So the only critical point that we're going to get out of this whole process is what? Is 3, right? The numerator is not going to produce anything. But even though there's only one critical point, we know that because of what we know about the function, that 3 there's no chance of it being a relative max or relative min, right? Because we know there's an asymptote there. But we still want to go through the process of putting it onto our sine line. We just have to state there is no relative extrema. Even if there's a change in sign there, we have to understand our graphs, our functions behavior, that even if there's a change in sign there, it's still an asymptote. This change in sign is not going to suddenly make it a relative minimum or a relative max. But as it stands, both intervals are producing negative slopes. So the only statement we're going to have is decreasing. Now, can I say that I have 2 negatives there? Can I say that my interval decreasing is from negative to positive infinity?
Nope.
Okay. There's got to be a break, right? Because that asymptote is causing that break. So negative infinity is 3, and then from 3 to infinity, because f prime is less than 0. Okay. No relative extrema. Okay, let's go to the next page. The bottom is talking about f prime graph. I'm going to save f prime interpreting derivative graphs a little bit later. So I'll save that for either Thursday or Friday. Let's go to page 22.
What would a relative extreme look like?
I'm sorry?
What would a relative extrema look like if it was something?
Oh, there would be no relative extrema in this problem.
But how would we know if there was one?
We would know there would be one if, first off, if this point exists, which will be coming from the numerator of our derivative, and if there's a change in sign,
Okay.
positive slope followed by
okay.
negative.
Okay.
Okay, page 22. Okay, so I want us to observe these curves here. So this is it says concavity test, but I'm going to rephrase it. I'm going to say this is a test for concavity. So you've seen and heard concave up and concave down. So let's observe both these curves here. These curves are obviously different, but what's this? What's the slope of this curve? Positive or negative slope? Positive. How about this one? Also positive, right? Also positive slope. But there's a distinct difference here, because here, if I were to look at the slopes of tangents, right? Maybe this is a slope of 1/2, then 1, then 2, then 3, then 4, right? So these are all positive slopes, but we can see that the slope is moving towards a positive direction. Here, the slope may start off with a positive steep slope, but then it's going to kind of gradually move towards 0. So maybe this is slope 3, then 2, then 1, then 1/2. So that movement of the slope is causing the curve to be shaped differently. So are both these functions increasing? Yes, they are. But what do you know about their derivatives? The rate of their slope is different, or the rate of their slope is changing. Okay. The rate of their slope is changing differently. Yes. Yes, yeah. So we're going to be gathering this data from second derivative. Yes, yes.
Rate of slope. I thought it would be just the slope is changing. Their second derivative is changing.
Yes. Or how about this? Yeah. So this.
The rate of the
Okay, let me revisit this later. But basically, we know that the slope patterns are changing. Okay, slope patterns are changing. One is increasing, the other is moving towards negative. So this is what we can say. Whenever your slope is moving in the positive direction, when your slope is becoming more positive, it's going to create this concave up shape. Right. If your slope is becoming more negative, then your graph is going to take on this concave down shape. It's going to be looking more like an upside down U shape. So just to kind of show you why or how this slope is becoming more positive, I'm just going to pull what I'm just going to pick out some slope values. Okay. So this is a pretty steep negative slope. So let's say this is a slope of -4. Okay. Then it goes to -3, then -2, then -1, then 0, and then 1, 2, 3, 4. If you look at these numbers here, all these numbers are moving towards a positive, right? It's a combination of negative and positive numbers, but the pattern is clear where all these numbers are moving towards a positive number, right? They're becoming more positive. So whenever my slope is becoming more positive, it's going to take on this U shape. Right? Likewise, if my slope is starting positive, and but if these numbers are headed towards the negative number or becoming more negative, it's also a combination of positive and negative slopes, but the curvature is that it's going to, as that becomes more negative, it's going to take on this upside down U shape, and we call that concave down. So a lot of this we're going to pull from the second derivative function. So the second derivative function is going to give us information about concavity, and it'll also give us information about what this transition point called the point of inflection, which I'm going to abbreviate as POI, point of inflection. So point of inflection is where that transition between concave down to concave up occurs, or from concave up to concave down, where, so here, if I were to look at the slope here, maybe this is slope 4, then 3, then 2, then 1, 0, -1, -2, -3. At some point, that slope is going to start moving in the other direction, -3, -2, -1. So at that transition point is where point of inflection occurs. You can also think of it this way, where if you were, imagine you're on a roller coaster ride, wherever the steepest part of your roller coaster ride is, that could be your point of inflection. Okay, that's where that maximum steepness is going to occur, and then it's going to start to gradually flatten out. So you can think of the point of inflection as that connecting point between the two curvatures. You can also think of point of inflection as where the steepest part of your graph is going to occur. So we're going to find this second derivative function. We're going to create a second derivative sine line. And the second derivative sine line is going to give us information about the concavity, the curvature of the graph, where the curvature is going to change. So we're going to create a different set of information about the same graph, right? The first derivative sine line will give us the information about when the graph is rising and falling. And then the second derivative is going to give us information about more detailed, more subtleties in terms of how is the curvature changing along that path. Okay, so here are the steps. We're going to set f double prime equal to 0. We're going to set the numerator and the denominator of f double prime equal to 0. And we're going to find those critical points. And then we're going to test values in each subinterval. And if there's a positive interval, then I'm going to use a U to indicate that that portion of the graph is going to have a U shape. If I get a negative concavity, that means my graph is going to resemble this shape. And if there's a change in concavity, I know that there must be a point of inflection here. And here are the because statements that we're going to practice writing. If we have an interval of concave up, we're going to say because f double prime is greater than 0. If we see an interval of concave down, we're going to say f double prime is less than 0. And then if there's a point of inflection, then we're going to just say f double prime changes sign. So you don't have to specify the order of sign change. You just have to indicate that there's a sign change. If you do say change from positive to negative or negative to positive, that's fine. You won't get points taken off if you specify the order, but you don't have to specify the order. Okay, so let's look at example 1 and see if we can go through one of these problems here. So it says find the points of inflection and let's say intervals of concave up, concave down. Okay, so to get to anything dealing with points of inflection, concave up, concave down, I have to make my way down to what? Which derivative? Second derivative. Yeah, so go ahead. Let's see if we can work our way down to f double prime. set f double prime equal to 0. And then find your critical points. Okay, take all those critical points and plot them onto your second derivative sine line. Right. We're essentially doing the same process as first derivative test. It's just that now our critical points represent something else. Instead of representing relative max, relative min potential, now these are all point of inflection potential. And then instead of the intervals telling us where the graph is rising and falling, it's telling us where the interval is experiencing the curvature of concave up or concave down. Okay, I'm just trying to pick as easy of numbers as I can find in each subinterval. I'm going to plug them all into my second derivative function and gather the signs. Okay, so if I plug -1 in here, I'll get negative times positive. So 2 negatives makes positive. My graph is going to be concave up in this subinterval. Plug -1/4 in here. -1/4 will be negative times negative. And this will also give me negative because 4 times 1/4 squared is going to be a number less than 1. So that's going to be 3 negatives. 3 negatives gives me negative. 1/4 gives me positive. And then 1 gives me a negative. So based off of this sine line, how many points of inflection do you see?
3.
3, yeah, because there's a change in sign in each of these subintervals here. At 0, there's a change in sign. At 1/2, there's a change in sign. There's 2 intervals of concave up. There's 2 intervals of concave down. And we also want to practice writing out our because statements. Okay, there's one more thing that I want to squeeze in for today, and that is something called the second derivative test. Now, you may be looking at this and thinking that this is called second derivative test because we're using the second derivative function, but this is not called the second derivative test. This is called the test for concavity. So the second derivative test is finding something else. Okay.
On the statements, would it be f double prime of x is concave up or f of x is concave up?
F double prime is greater than 0. F double prime is less than 0. F double prime changes sign.
But on the first one, like at the start of the statement, it said f double prime.
Oh, sorry. Yeah, you're right. You're right. It should be f of x. F of x is concave up, and f of x is concave down. You're right. Yeah, so the function is concave up. The function is concave down. Sorry, it shouldn't be f double prime here. Yes, question.
Yeah, I was just wondering what the point of the second derivative test is. Because it says it changes to.
Yeah, that's right. So let's go to page 23. So what's a little strange about second derivative test is that it does the same thing as the first derivative test. It finds relative max and relative min. It doesn't find concavity. And you may be asking, well, why do we need this test if we already have something that can handle relative max, relative min? And the answer to that is many times you're not going to need this because the first derivative test is going to be the one that you're going to prefer to use. But we still need to have knowledge of this because sometimes the problem can be on the AP exam where they're forcing you to have to use knowledge of second derivative test. You don't have enough data to use first derivative test. Good. Yes, I'm gonna go over that, right, in terms of what that could look like. So again, it's a test for relative max and not a point of inflection. And it achieves the same thing as the first derivative test. So here's what I want to kind of talk about to begin with. Okay. So let's say I found f prime, okay, and I found that an f prime is equal to 0. So let's say I found the critical point where there's a slope 0, okay, but I don't know whether that is a relative max or relative min. Okay, so we're still going to go through the same steps. We're still going to set f prime equal to 0. We're still going to find our critical points, but instead of creating a sign line, we're going to do something else. So let me ask you this: f prime of, let's say this is 1 here. What's the slope here? F prime of 1 will be equal to what? Will be equal to 0, right? The slope is 0. What if I ask you for f double prime at 1? Okay. Is this part of a concave up or concave down graph? Concave up, which means that f double prime of 1 should give me a positive number. So here's the big idea here. If my slope at that point is 0, without looking at any other slopes around that point, if I know this point is part of a concave up graph, meaning that if I plug a 1 into the second derivative and get a positive number, then that must show me that it's a concave up graph. If I pair a concave up graph with the slope 0, there's no choice but to call this a relative what? Relative minimum. So if I can gather these two sets of information, a critical point from f prime and a concave up from f double prime, then I can conclude that that point must be displaying a relative minimum without going through a slope sign. Likewise, what if I had a graph that looked like this? Let's say this is 2 here. F prime of 2 would be 0 because the slope will be 0. And then f double prime of 2, would it be positive or negative?
Negative.
It would be negative. And so if for some reason you didn't have the graph in front of you and you're plugging into your second derivative and you get a negative number, you know that, okay, if this x value 2 is part of a concave down graph and that point has a slope 0, then the graph must be looking like this and I must be looking at a relative max. So let me show you what an AP exam question could look like, where you're using knowledge of second derivative test. And we'll do this example below a little bit later. But here's an example. Okay, let's say our function is continuous and differentiable everywhere. And this is the only data that they give you. F of 4 is equal to 3. F prime of 4 is equal to 0. And F double prime of 4 is equal to negative 12. Okay, so the order pair is at 4, 3. Some point here. What does this tell us? That point is experiencing what? A slope of 0. So it could be a relative max, could be relative min, could be neither. But this is what's going to help us to determine it. F double prime is equal to negative 12. That negative 12 is kind of abstract. We don't really care about that number. We care about the fact that it's what?
Negative.
Negative. So if it's negative, that means the graph must be concave what?
Down.
Concave down. If I pair concave down and slope 0, I must be looking at a what? Relative max. So that is an example of an AP exam question where you're using knowledge of second derivative test. First derivative test won't help you out because you have no information about how the slope is behaving on either side of 4. You have to rely on the second derivative test. Okay, final thing is this can be confusing for students because why do you think that a lot of students want to say that there's a relative minimum here instead of relative max?
Negative.
They see the negative, they feel, oh, that's a small number, that must be a relative minimum. But it's opposite, right? This is talking about the curvature, it's not talking about a location. So these sometimes get mixed up between students because they see, oh, positive number, that must be a high point, must be a relative max, but that's the opposite. Positive concavity is going to be a relative minimum. A negative concavity is going to be a relative max. So just understand that that's a point of confusion and mix-up for that student's experience. Okay, I didn't quite get through a full example of second derivative test, but this is, I wanted to show this to you to show you that this is how an AP exam can involve a second derivative test. Okay, so check your calendar for your homework. Tomorrow, we will move into curve sketching and first derivative graphs. All right, come get your phones. There you go. Thank you.
Thank you.
It comes in the back, so we can figure out.
I will, because I don't know what I'm doing.
So we do